So what I will be speaking on today is sort of the science behind the Iron Man suit. I've told my children that this is what I do at work, and they tell me that that's very interesting, but they would like me to bring it home. And of course I tell them that that's classified. But my wife, who's sitting in the front row, she tells me that I'm overselling it. But that may be, but we sell it as hard as we can. So today the work that I'm going to present is part of this center here, the Center for Materials at Irradiation and Mechanical Extremes. It's what's called an Energy Frontier Research Center, funded by these guys, the Department of Energy, the Office of Science, Basic Energy Sciences. So this is going to be a culmination of about 5 years worth of work of a broad team of experts that contribute to this, and we'll talk about them in just a moment. So this is a bit of an eye chart. This is all of the people who are involved in this center. Now I'm not going to go through everybody here. Of course, I sit right here as the experimental lead in the mechanical extremes thrust. Many of the folks who are on this chart are here in the audience today, and I'll point out their work as we go along. But what I really want to point out here is that the work that's done here, there's about 20 LANL staff involved that make up 4 full-time employees. However, there are 8 faculty from different types of universities, University of Illinois, MIT, Nebraska, also the University of California, Santa Barbara. But really the people who do the heavy lifting here are the postdocs and the students. Nearly 25 postdocs and students are involved with this. So us folks who are staff and faculty, we're guiding this research. We're working with the young folks who are actually doing all of this work. So, can't get into this without getting into Iron Man and, of course, Captain America. Now, this is some of the inspiration for the types of materials that we're making, because what we're trying to make are materials that are indestructible. And, of course, Captain America and Iron Man have a distinct interest in materials such as that. We can think about what would Captain America be without his shield. Well, judging by the damage on his shield right now, he'd probably be shot. Iron Man the same way. What would Iron Man be without his Iron Man suit? He would be Robert Downey Jr. in his pajamas. So these fantastic properties that we're talking about here today are going to be ultra-high strength, self-healing materials under irradiation conditions, and also resistance to shock deformation, everything that Captain America and Iron Man would be interested in. But of course, you don't have to take my word for it. President Obama, back in February, also spoke on this topic. I'll see if I can get this to play.
This is John's service, and we're going to miss you. Now, today I am joined by researchers who invent some of the most advanced metals on the planet, designers who are modeling prototypes in the digital cloud, folks from the Pentagon who help to support their work. Basically, I'm here to announce that we're building Iron Man.
It's not just me, folks.
I'm going to blast off in a second. This has been a secret project we've been working on for a long time. Not really. Maybe. It's classified. But keeping America at the cutting edge of technology and innovation is what...
So what he was announcing there was a manufacturing hub, and we'll get a little bit into what those are and how that affects what we're talking about today. But to get back to what we're going to speak on is on the development of these nanocomposites for extreme conditions. And so we'll start talking about material science and engineering and nanotechnology. We'll move on to talk about specifically this class of nanomaterials that we're looking at here. What makes them so strong? We'll talk a little bit about the physics that goes into that. We'll talk about using these materials for shock deformation, high temperatures, and radiation damage tolerance. So in nanotechnology, we're very fortunate in that we have a starting point for exactly when nanotech started, or at least what we think of as nanotech. And it comes from Richard Feynman in a 1959 lecture at Caltech. And this lecture is regarded as the basis of what we call nanotechnology. When he gave this talk, he said, What I want to talk about is the problem of manipulating and controlling things on a small scale. If you look it up in Wikipedia, that's the definition of nanotechnology. This is what he looked like when he worked at LANL in 1943 on the Manhattan Project. He then went on to have a successful career, Nobel Prize in Physics in 1965. He also is such a popular scientist that he's had a movie made about him. This movie called Infinity, if you want the combination of a love story and science, which scientists love, this is what you're going to want. But other insight that Feynman has are these fantastic one-line quotes. What do you care what other people think? I mean, that's some information for life right there. But to get more technical, we can talk about some of the quotes from Feynman's lecture back in 1959. He brought up the question about better electron microscopes, which we use to see what happens to matter at the atomic scale. I put this out as a challenge. Is there no way to make the electron microscope more powerful? Back then, he couldn't see individual atoms with an electron microscope. And I'll show you that now we are at that point. Miniaturization by evaporation, putting atoms down in a certain arrangement. Evaporate one material, then evaporate the next material, then evaporate another. Rearrange atoms. What would happen if we could arrange the atoms one by one the way we want to? What could we do with layered structures with just the right layers? 50 years ago, these questions were being posed that only now are we starting to really answer. So we talk about electron microscopes. Here's a transmission electron microscope. Rob Dickerson, who's the head of this facility, working on that electron microscope. We see a material here. This is copper and niobium, and this is the interface between it. All of these little white spots are individual columns of atoms. So this challenge, to a large extent, has been met 50 years later. Can we miniaturize by evaporation? You bet. Kevin Baldwin, who's sitting in the back of the room, actually runs this type of equipment, these vacuum deposition systems that exactly do what Feynman envisioned 50 years ago. We'll talk a little bit more about that in this lecture as well. But the motivation goes further back than just Feynman. When we think about material science and engineering in relation to society, we define our history by the materials that limit our potential. Stone Age, the Bronze Age, Iron Age, Chemical Age, nuclear, composites, aerospace, submicron materials age, all of our potential as a human society is limited by what materials we can make. And so if you actually want to get involved in a field where you can make these types of differences, material science may be one of these places for you. So let's talk about what is material science and engineering. So this is what you would get in an intro to material science and engineering course. You would learn that structural materials, or materials in general, are broken up into structural materials and functional materials very broadly. Structural materials are for load-bearing applications, things like cars, airplanes, and so forth. Functional materials are electronic, magnetic, optical, or chemical types of phenomena. Now in this case, there's a lot of overlap between these two things. You can imagine if we make our iPhone down here and we drop it on the ground, which is this, we want our iPhone to still work. And so there's no hard and fast lines between these two areas. So also what you would see in your classroom is that the material science and engineering is also broken up into what we call the materials tetrahedron. So the base of this tetrahedron is synthesis and processing, how do we make a material, structure and composition, what is it structured as, and then the properties of that material. Making those ties is what we would call material science. How does that then perform as a car, as an airplane, as an integrated circuit, and so forth, is where we start really engineering things for a specific application. So that's where the science and the engineering kind of comes together. Now we can look at this even more broadly in terms of structural materials, which is what we're going to talk about today. We can think about buildings, bridges, transportation, power generation, nuclear reactors. We'll touch on that today. Thin films and micro electromechanical systems. But what we will really focus on here is making lightweight structural materials for transportation and also radiation-resistant materials. Other folks, especially here at Los Alamos, also work on biomaterials and soft matter, and also within the functional materials realm. So the research that we've been doing here kind of started it started with Feynman, but then the specific programs that we're working on, if you think about the National Nanotechnology Initiative. That was back in year 2000 or so. That's when nano was the hot thing to be doing. As we moved on in time to about 2008, 2009, the question was how do you take these unusual phenomena at the nanoscale that we were researching here, and how do we make those to make materials that perform under extreme conditions? How can we harness that for an energy type of application later on? So as a result, what was funded back then were 46 Energy Frontier Research Centers. CMIME, which I'm speaking about now, was one of them. 5 hubs were made for these in different areas. Today, where we're at is manufacturing, which is how do we take what we've learned over the last 15 years and start actually making product out of them? How do we push towards making something that makes a difference for society? So we'll touch on this in a little bit more later on. But advanced materials was something that's been called for across all of these different programs. And so what we want to do is develop these advanced materials, which are defined, which the effort is defined by developing low-cost production methods for lightweight materials, carbon fiber composites, for applications that will improve fuel efficiency, performance, corrosion resistance for transportation. And other examples are novel materials for improved manufacturability for solar or integrated circuits. A lot of work to be done there. I don't think we're going to be short of a job anytime soon. So let's start talking about fuel savings and lightweight materials for energy efficiency. Now, some of you car buffs might recognize this is a much awaited 2015 Ford F-150 pickup, which the new things for it, I mean, one thing that's new is it's got these cool LED lights. The other thing that's cool is that all of the body panels here are being replaced with aluminum for a 700-pound weight savings. So what does that mean? How does it help energy efficiency? Now, if you ask the EPA, they estimate that for every 100 pounds that you save, you get 2% better fuel economy. That means if you make your truck lighter, you're going to get a lot better fuel economy. It also means that if I lost 50 pounds, I would get about 1% better fuel economy. But also, we can look at it in a different way. If we drop 20% off of the weight off of a compact car, like a Honda Civic, Toyota Corolla, something like that, you'll get about a 13% increase in fuel economy. This is according to the Aluminum Association of America. So we can imagine in a car, we've got 30 miles per gallon, 12-gallon tank, so small fuel tank. You can get from Los Alamos to Denver on fumes. You will coast into the gas station. If you drop your weight by 40% with that same amount of gas, instead of driving from Los Alamos to Denver, you're now going to be able to get to Laramie, Wyoming, and have plenty of gas to spare. That's the difference that you get by dropping the weight. And all you have to do here is just buy the car that's lighter. You don't have to change your driving habits. You can drive just as fast as you used to. Doesn't matter. You will be able to do this without doing anything other than changing the car that you purchase. So, how are we going to get there? We're going to make strong, lightweight nanomaterials is what we're going to do. And the question is what makes this class of materials so strong? So the strength of a material is defined by how hard it is to be able to move the atoms around into the arrangement that you want. Now there's 2 ways of looking at it. The first one is this theoretical strength, which would be the upper bound of how strong something can be, versus the strength of real materials. Now the strength, this theoretical strength, if you imagine 2 layers of atoms here, and we try to shear them and just try to move them like this, what you find is that the upper bound is determined by its stiffness divided by some factor. So what that means for copper, if you were to just rip these atoms apart, you would have this number here, 7,000 megapascals as the strength of this material. In reality, it's 7,000 times weaker. So the question is, well, why? Well, real materials have these defects known as dislocations, which ends up lowering the real strength of materials. But you can form a hypothesis. All right, well, if this is the case, a dislocation-free material should be very strong. And indeed, you can test that. In fact, it was tested back in 1958 on perfect copper whiskers, which were very, very fine little wires that have absolutely no defects. They're perfect material. And what happens when you load this, so this is stress, this is how hard you're pulling on it. You pull on it, you pull on it, you pull on it, and then all of a sudden it drops and the strength is very, very low as you continue to pull on it. And the reason for that is this material that had no defects right here, you hit this stress and then we generate defects, and those defects limit the strength for the rest of the deformation. So this is one way of looking at it. Another way of looking at it is if we imagine this kind of experiment, which is called a bubble raft experiment. These are actually soap bubbles that are on top of water. You can actually do this experiment in your bathtub. So in this case, this is a representation of a close-packed spherical structure, which is also what you can end up seeing in materials such as copper. Now, when we look at the columns of atoms here, what we find is that right in the middle here is this extra half plane. This extra half plane is a dislocation. And it's the motion of these extra half planes that dictate the strength of a real material. So, as Sir Charles Frank, one of the founding fathers of material science, said, materials are like people. It is the defects that make them interesting. It's also what material scientists get paid for. So, so a way of looking at this schematically, if we imagine again our columns of atoms, we've got our extra half plane right here. We've got atom 2, atom 3, and atom 1. What happens here is as you apply a stress to this material, what happens is individual bonds break and are remade from one step to the next. So in this case, we broke 1 to 3, we form 1 to 2. You can do that again, and then you can do that again. And what you get at the end is this step at the end of our material. You repeat this billions and billions of times, to use Carl Sagan's terminology, and you'll actually be able to bend your paperclip. This is the basic physics that occurs for bending paper clips. It's what happens in car crashes. You name it, this is what dictates it. So there's another way of looking at this. It's a little bit easier to understand, at least for me. This is the Goldie the Bug treatment of dislocations. This was done by one of my professors, actually at UC Davis, Jim Shackelford. And the way that he looks at it is that if you have Goldie the Bug, which is some kind of caterpillar-y thing, and you have bonds that are represented by Goldie's legs here, if you try to just rip Goldie by pulling on her antennae, it's very difficult to move Goldie. And Goldie's none too happy by the time you make your one little step here. However, if you move Goldie with a defect such as a dislocation, you give Goldie a swift boot in the behind right here, you break one bond, she gets kind of this kink in her, and then this bond can be gradually moved along. And so you can see that here. Goldie's much happier at the end. We end up seeing that we have our step here. And this is the way that real materials actually deform. So when we talk about real materials, in terms of making a material stronger, one way that we can do it is take these defects that are known as dislocations and make their lives miserable. So what we can do is put in obstacles. Obstacles such as grain boundaries. Real materials are made out of grains, just like grains of sand in a lot of cases, metals that are used for structural applications. You can also put in a boundary, like a twin boundary here. So in this case, you've got mirror symmetry across this twin boundary. If a dislocation has to come in this way, it has to change directions and move this way. It's like a speed bump for a dislocation. In our case, we're going to look at one other specific type of interface, which are these interface boundaries, which is a planar boundary separating one material A and one material B. We represent dislocations in structural materials as little upside-down T's. I don't know exactly why. So what happens if we put a whole ton of these boundaries into the material? Well, we get this plot that we can see right here. So these are different types of copper-based materials, and this is what their strength is. If we talk about a single crystal of copper with dislocations in it, the strength is extremely low, a couple of megapascals in this case. As we start introducing grain boundaries, that is, having a grain size of 10 microns, this is like the copper that you buy at the hardware store. You'll get a strength right about here, about 10 times higher. If you start dropping that grain size within the material to 200 nanometers or 0.2 microns, you'll get a strength up here. If you start doing materials that are only 2 nanometers in layer thickness, in the case of copper niobium here, which there's actually a transmission electron micrograph here, just like Feynman was pushing for. In this case, you've got materials that are only about 5 or 6 atoms thick in each individual layer. The strength of this approaches that of what you would expect for a perfect crystal. So these are the types of materials that we're trying to make. And so the key thing to take home here is by reducing size, we get more interface area per unit volume, and the properties start being determined by the defect interface interactions rather than what you actually made the material out of to start with. It's all about the interface at that point. So what do I mean by that? So we can talk about this new paradigm in the way that materials perform. We call that interface-dominated behavior. So when we think about a layered composite, typically what we have are these things called constituent-dominated behavior, where the phases of the material that you start with, metal A and metal B, dominate the nucleation, storage, recovery, and blocking of defects such as dislocations. That's what dictates the properties that you get out. Now, if we start adding more and more interfaces, what we find is that the interface dominates these processes. And as such, it doesn't matter so much anymore that you make a material out of copper and niobium, silver and copper, zirconium and niobium. What starts mattering is what the interfaces are between them and what their structures are. You can imagine that this gives us boundless potential for changing the properties of materials and controlling those material properties just by forming the correct kinds of interfaces, just like Feynman said. So again, you don't have to take my word for it. Seeing is believing. This is a copper niobium multilayer. The center here is copper. This is niobium here. This is niobium here. This is work that Nan Lee does, who's also here in the room. Nan, where are you? He's right over here. So this is work that he does in the electron microscope and deforms this material and watches exactly what happens to the dislocations as they move through the material. So what you're going to see here is that the interfaces are going to emit different types of defects. Oh, sorry about that. Can't actually see this thing. Play. There it is. So what you're going to find here is that there's going to be defects that come across, like this one here, from one interface to the other, one interface to the other, one interface to the other. So you can imagine that if the motion of these defects dictates the way that the material behaves on a bulk scale, these types of interactions that are happening at the interface form the basis of the properties that we'll measure later on. So this isn't a new concept. Multi-layered materials have been used for a long time in the form of Damascus steel. It was used in Middle Eastern sword making, developed around 300 BC in India. So these are also called pattern welded steels. You get these very nice swirl patterns from the processing. But the sword recipe was lost around 1800. Nobody knows exactly how these swords were made. But just recently, some researchers in Germany took a chunk of one of these ancient swords, dissolved it in acid, and was left behind with a whole bunch of carbon nanotubes and also cementite nanowires. So back in 2,000 years ago, they were using nanotechnology to make super strong, super sharp swords, but they didn't know it. They didn't know that it was nano. The thing that allowed us to know that it's nano is, again, the transmission electron microscope. This is the TEM, just like Feynman said that we needed to be able to discover these sorts of key strengthening mechanisms. So in this case, though, the super hardness is lost after annealing. There's no radiation damage tolerance, so we're not going to build a nuclear reactor out of Damascus steel anytime soon. But they have been doing nanotechnology for a long, long time. So in our case, we can do this in a much more controlled fashion. So this is work that Kevin Baldwin does in his laboratory, where he uses a vapor deposition process called magnetron sputtering to make these bulk foils of nanocomposites. And so what he can do is he takes a substrate, puts a piece of silicon, it could be a piece of silicon that he puts here, and then rotates the stage to one gun or another that deposits, say in this case, copper and niobium. So you'll rotate to gun 1, deposit copper, rotate to gun 2, do this with niobium, and then come back to gun 1 and do this over and over and over again until you build up a film that looks like this. So I can actually pass one of these around. This is a 20 nanometer individual layer thickness film with 1,000 layers. So it builds up a foil that's 20 microns thick. And so this is actually sitting on a silicon substrate that we've detached the foil from. So you can take a look at that. So you can see that we do get a material that you can use as a hard coating. You can do small scale tensile testing, micropillar tests. We'll talk about what those are in a minute. But all the way through the thickness of that material, you have this type of layered architecture of copper and niobium. What this allows us to do is we can change the length scale really easily in the range of nano to micrometers, and we can look at specific different types of interfaces. So there's another way that we can make these materials too, and this is taking inspiration from the ancients who were making those Damascus steel swords. So if we can imagine two sheets of material, copper and niobium in this case, we can actually look down at the schematic here. We take copper and niobium, we roll them through a rolling mill. You'll see a picture of one of those in just a moment, and they'll bond together and make a very long sheet, like you can see our student Tom Nozolek holding right here. Then you cut that up, stack it again, and roll it again. And you do this over and over and over again, which is why it's called a cumulative roll bonding. And what happens is you start with a material that looks like this, with layer thicknesses of millimeters, and you can drop all the way down to 9 nanometers in layer thickness. So a little bit of nano trivia here. So we can now make these kilograms of nanomaterials, essentially nanomaterial or nanocomposite in the quantity of something that looks like a ski. And what does it mean to be able to roll this out to this point? Well, if we were to take a nickel, which is the same thickness as our starting materials, and roll it out the same amount that it takes to make this material, we would have to roll it out 2.2 kilometers, almost a mile and a half, in order to be able to get to that point. So we've really, really tortured this poor material. But you'll see the types of properties that we can get out of this are not the same as what you would expect with copper or niobium alone. So what are some of those properties? Here's just a quick summary. When we start making a nanocomposite like this, we can control deformation mechanisms. We won't touch on that so much today. We will touch on outstanding damage resistance during shock, outstanding thermal stability. These layers don't break down after heating to very high temperatures. They're ultra high strength, and they're outstanding radiation damage resistance. So in this case, this is what you want for your Iron Man suit. This is what you want to build your car out of. These types of materials that are very damage tolerant. So what we're going to do today is look at the difference between the materials that we can make by this type of synthesis technique compared to what we make by a cumulative roll bonding, which is made in a rolling mill that looks like this. So you can see these big rolls that we have. There's actually one down below this table too. This is about 18 inches in diameter, and we feed our strip of material into here and essentially crush it until the material bonds. So the issue here is that if we make different types or if we use different synthesis techniques, we'll get different types of interfaces. So we can form a hypothesis, and that's that the atomic structure of an interface dictates its mechanical response. Interfaces with different atomic structure will give you different mechanical behavior, and if we can change the synthesis route, we can get preferred interfaces with superior properties. So before I move on, I actually brought a chunk of the material that we make by this roll bonding process. This is just a small piece of one of those skis that Tom Nozolek makes. This is 60 nanometers in individual layer thickness, and there are 65,536 layers, give or take a few. So I'll pass this one around as well. But you can see that it's a bulk material. This is something that you can start actually using in a manufacturing type of process. So what types of interfaces? When we say the interfaces are different, how do we describe them? Well, there's 5 parameters that you use to describe a certain type of interface. 3 of them are used to describe the orientation relationship between crystal A and crystal B. And I've actually brought a couple of crystals here. Well, big crystals. One of these is niobium, this one. This one here is copper. Now the orientation relationship is how these are rotated relative to one another. So it takes 3 parameters to describe that. Then what we find is that if you put these 2 things together, there's an infinite number of ways that you can cut an interface plane. And so the way that you describe that is how you put them together. Do you put them together like this? Do you put them together like this? Do you put them together like this? All of these parameters are described when we talk about what types of interfaces that we have. And what you're going to find is that in the roll bonded material and the physical vapor deposited material, you'll get very different types of interfaces and different types of properties. So how does this work? In physical vapor deposition, we get a preferred orientation relationship and interface plane, those 5 parameters, from thermodynamically driven processes. That is, they want to land and deposit in a low energy configuration. Now when we roll a material, that's not necessarily true. What happens is that the grains in the material, as you roll just a pure material, will rotate in a certain way depending on the degree of slip that it has on certain slip planes, so how those dislocations move through the material. When we really do extreme deformation, what we find is that we get grain boundaries that have high misorientation angles, disordered structures. So the thing to take home here is that you can get kind of a mess when you deform a material as opposed to something that's very ordered when you vapor deposit a material. But what we're going to find is that actually you can control the types of interfaces you get fairly well with the roll bonding type of technique. So what happens when we do this? So if we take our material, copper, niobium in some cases here, and we roll them by severe plastic deformation technique, we roll them out very, very far, what we find is that we can ask some questions. Can the interface character stabilize in extreme strain, giving you a certain type of interface that's preserved with further strain? Do you get a broad distribution, like if you were just to roll copper or niobium alone? Or do you get a single preferred interface, like you see in physical vapor deposition? Is it texture driven, that is driven by slip like in rolling? Or is it interface energy driven, as you would see in physical vapor deposition? And are these interfaces sharp and ordered or all jumbled up? So the key finding here, I won't get into the details of this, but what you have is this competition between orientational stability and interface energy. What does that mean? It means that when you roll this material out, you have to have these crystals not reorient as you roll them, and they have to have a minimum energy. You don't want a highly energetic interface that would form during this process. So if you satisfy both these conditions, then you should only get a few interfaces. And the fact is that's exactly what we see. And these are the types of interfaces that we're going to talk about with the rest of the talk today. So this is the physical vapor deposited interface. And in this case, here's niobium, here's copper. And you can actually do these molecular dynamics simulations as well that match the structures that we see very nicely. But what you see are these atomistically flat types of interfaces in both the model and the experiment. And the way that they're made is by taking our crystals here, copper and niobium, and joining them along their close packed planes and directions. So then we join these two together in what's called the Kirchhoff-Sachs orientation relationship. It's something that's very common for these types of materials. If we look at the roll bonded interface, what we find is that we get something that's very, very different. So you can see here that this interface is serrated. It has these little ledges between the copper and the niobium. So instead of it being flat, now it's got these kind of teeth that lock it in place. And so in this case, it's actually the crystals are in the same orientation relationship. All we've done is instead of joining them like this, we're now joining them like this. And so we join them along their 1-1-2 planes in this case. So very different interfacial structures, and we're going to see that the properties that we measure are also very different. So we can visit our hypothesis using these two different types of interfaces. So what we're going to do first is we're going to squish this material in this direction, perpendicular to the interfaces, and see what happens. Now we're going to use a technique called micropillar compression. Why it's called that is if you look at the diameter of these deformed pillars, this is only 3 microns. A human hair is approximately 100 microns. So this is about 30 times smaller in diameter than a human hair. We can do these tests using specialized equipment. You'll actually see some videos of ones that we do in the electron microscope. But what we find is that as you press on the material, it will load up. So this is stress. This is a measure of strength. And then it will yield at a very high stress. The material here, these 2.5 gigapascal stresses, are about the same as you would see in a tool steel. Although you are making a material out of copper and niobium, two nominally soft materials. All you've done here is just add a whole lot of interfaces between the two phases. That's it. So you can make materials as strong as steel, starting with materials that are intrinsically soft. Now, one interesting thing that we see here is after we load up the material, what will happen is this band will form, and then the thing becomes softer and softer as we deform it more and more. And you can see that band right here. So the question is well, why is that band making it softer? Is it just breaking our layers as this band grows? Because, well, our layers are what make it strong, so if you don't have any layers anymore, that would make sense why it would be weak. But the answer is actually if we section this, we can actually go in using a focused ion beam, and we can section this into a TEM, or electron microscopy sample. And we can look at the structure of this band. And what you see is if you start on one side of the band and go to the other, it's continuous across the entire shear band. We can look at it closer, increase the magnification. Here's our band again. And if we look at an area like this even closer, here's our band. The copper and niobium doesn't break up. It's still strong. So the question is, how is it softening? Well, one thing that could be happening is if the interfaces can slide like a deck of cards, that would make sense as to why this material gets softer as we form this band. So we can test that hypothesis too. We make these layers. We put in our layers at a 45-degree angle. We smush this, And sure enough, they fail right along those interfaces. We can measure strength relative, so this is the strength of this particular test. This is the strength when we compressed perpendicular to the layers. And what you find is that this material is actually much weaker in this stress state. So what we've been able to find is that the interfacial shear strength of this particular type of interface is extremely low. So what we found is that this particular structure, the interface dictates its mechanical behavior. The interface itself is weak in shear. If we imagine crushing this pillar, we rotate our layers a little bit on the corners, just as it's just the way that the stress state of the pillar compression test works. And then we form this single shear band, and that coincides with this kind of softening event that we see. So the questions are, what happens if we change the interface? So we'll move to this roll bonded interface and crush it in the same way. Now in this case, we see very, very different behavior. If we load it, take a picture B, and then unload it, load it, we take a picture C, unload it, load it again, take a picture D, and then by the end of the test it looks like this. What you find is that we didn't get that stable shear band anymore. The material didn't soften as we deformed it. And the question is, well, why not? We can section that material too, and sure enough, the layers have broken up. They didn't form this stable kind of deck of cards that could just slide. And the reason for this are the different interfacial shear responses. If we think about our PVD interface, which was weak in shear, this is the one that just formed a nice sliding type of interface, it's flat. And if you were trying to move this along this deck of cards, you can move it in almost any direction, and the stresses to do that are relatively low. That's what this line here represents. So 600 MPa, 700, 600, something like that. The ARB interface, that roll bonded interface, is serrated. It locks things into place. The shear strength is extremely high, out here close to 2,000 megapascals or so. So what that means is that you can't slide this interface effectively at all. So that mechanism that we saw where you get a stable kind of deck of cards sort of sliding can't occur. So what we found here is that the roll bonded material has a similar morphology and chemistry, very similar types of layered structures, but the interfaces themselves are different. And what that does is completely changes its mechanical behavior. So now another question is, well, what happens if we take these interfaces and squash them this way? And so we're going to do those experiments, this time in a scanning electron microscope. So you'll actually see this material deform as we collect the data. So this one is a physical vapor deposited foil that has been, again, fib milled into this configuration. We've got a punch that's going to come down and smash this thing, and this is all done in a scanning electron microscope. So what we'll see here is the load display, or the stress strain data that we can get here as we deform the material. So this is the physical vapor deposited material. You see that the material loads up, and then it starts to deform. That's when this curve starts bending over. You can see this guy starts kind of bending over a little bit. It hits a maximum strength, and then as it starts to bend, it gets a little bit softer. And then we unload it. So in this case, you don't see much on the surface of this material when we deform it. Now let's look at that roll bonded type of material. You can actually see some of the layers have been kind of etched in the roll bonded material by the machining process that we use to make these. But what you're going to see is a very different kind of behavior. So we start loading it, we see the material starts to yield, you see some deformation, and then there's this load drop, and it corresponds to forming this band. It loads back up, it's going to show another load drop, and that corresponds to this band forming. So this kink banding mechanism allows us to deform this to very large strains without ever breaking the material. The material, it certainly becomes kinked and it's deformed locally, but it doesn't actually fracture. If you can imagine, this type of material, what happens is that we've got this very high strength here, still 1 gigapascal, but it can deform to very large strains a long way while maintaining that strength. It just kind of forms a kink band, gets a little bit weaker, and then hardens again. And so you can imagine that the amount of energy, if you made an entire plate out of this material, it would absorb a huge amount of energy as you squash this type of material. This is going to become important when we start talking about shock and how this material would behave under an armored kind of application. So if we think about how these kink bands form, this is like a classic physics problem, actually. It's been studied by physicists, geologists, and so forth. One approach is looking at boron epoxy composites, so like a very stiff fiber inside an epoxy matrix. And you can also get kink bands forming in those. That's usually associated with a fracture of those fibers. You can also test these. The geologists have done this with stacked lead metal sheets. So you originally stack them this way, and you compress this. And you can also see kink bands in this case. In our case, it's probably closer to what Orawan, one of the other founding fathers of material science, found in 1942, where he tested single crystals of what's called a hexagonal close-packed material, so in this case it's cadmium, and what he found is that he saw these here as well. And so the reason that he saw them was because dislocations in his material were only able to move in just a handful of ways. And so we think that's also what's likely happening in our layered composites, is that our layered structure is making the life of a dislocation so difficult that it only wants to move in one fashion. And so what we end up seeing is that usually we don't see kink bands because the material can slip however it wants. In our case, what we've done is made a geometry that's layered like this that only have a single grain across the thickness, and these grains are like big pancakes, so they don't have any boundaries within the layers. Contrast that with the PVD material, you've got lots of boundaries within the layers. And as such, we think what's happening here is that the nanolaminate structure is making these dislocations only want to move in certain directions parallel to the layers, and as such, you start seeing these new deformation mechanisms. So just to summarize here, what we find is that when we compress perpendicular to the layer direction, we see that the weak interfacial shear strength in the vapor deposited material gives us stable shear banding. If you change the interface to something that doesn't want to slide, you get very different fracture behavior. And when you look parallel to the layer direction, you can either get kink banding or no kink banding based on the types of microstructure that we have. So now, how does that affect things if we were to look at, say, an armored application or something that was being deformed during shock? So why do we care about shock? Well, lots of things we care about happen under high strain rate conditions. Crashworthiness, how does your car deform when you crash it? How does a jet engine handle damage if it fractures in flight? Of course, armor and penetrator type technologies, nuclear weapons, earthquake damage, laser shock on a surface, and so forth. So there's lots of things that happen at very, very fast timescales. So we've actually shocked these materials before. And what we found is that if we shock this with a flyer plate in a very carefully instrumented way, we can shock these to very high pressures and not see any sign of damage. It's almost indestructible at high strain rates under certain conditions. And you can take this type of data and you can write a very nice paper like one of our postdocs here did in Acta Materialia, and you can discuss how the complex shock wave interactions occur due to the layered structure. Or you can take this material out to the shooting range and do what I call the just shoot 'em approach, where you just take the material and you pop a bullet in it. And so what happens here is this is our material after it's been cross-sectioned, so you're seeing half of it. This is where the bullet path was. And what you see if you look at this red region in the microscope is you see these bands, which are exactly what we saw when we compressed that material in the electron microscope. So you see these kink bands. So understanding the kink bands allows us to understand why this material worked out so well by just shooting it at the range. So in the end, the idea here is that we will be able to develop great energy absorbing armor materials from these types of approaches. So we've just covered the lightweight structural materials for transportation. Now what we're going to do is move on to the radiation resistant aspects of these materials. So we're going to talk a little bit about high temperature stability and then radiation damage tolerance. So the motivation behind this, there's a whole bunch of basic energy sciences types of studies and workshops that put out these reports that gave these specific science issues. So how resistant to failure in extreme conditions of temperature, radiation, or environmental exposure can we make a material? How do we make a self-healing kind of material? Or how mechanically strong can we make materials yet keep them lightweight? We just talked extensively about this last point, but now we'll go ahead and touch on some of these other 2 points. So it turns out that this material also can take high temperatures without too much of a problem. What we found is that with the roll bonded material, you can have this layered structure before heating, 10 nanometer individual layer thickness, heat it to 500 degrees C, which is half the melting point of copper. That's one of the constituents. And what happens to this material? Nothing. If you're Iron Man in this case, you are in good shape. So you can even expose these materials to very, very high temperatures. This is the work of Shijian Zhang, who is also sitting right here in the 3rd row. And again, electron microscopy is really key to this type of work. Without this, you wouldn't know that these layers remained stable. So after we've heated it, we can measure hardness. This is how much your hardness goes down as a function of doing the heat treatment. This is our roll bonded material. It barely changes at all. This is if we do this to the vapor deposited material. It's not quite as stable. If you do that to a host of other nanomaterials, it won't retain its hardness. So that's good for nuclear reactors. And so if we think about structural materials for fission and fusion energy, lots of folks who work on these types of problems, what happens is you'll have an energetic particle come in from your reactor, hit your material, and it'll displace an atom. And then that atom will displace another atom, and so forth. You'll actually see a movie about that in a moment. But what you start forming are these things of jumbles of atoms that are called cascades. Now, after that cascade happens, all of these atoms sort of rearrange, and you'll have a few defects in the end. Some of them are called point defects, called vacancies. Some of them are called interstitial atoms. And what happens is that these vacancies can move around within the material, and if they coalesce like this, they form voids. And of course, voids are bad. Voids swell your material. You can imagine here, this is an unirradiated material. This is a material that's been irradiated to a certain dose. And you'll find that your parts get longer, or they get fatter. That's not good for an engineering application. You design for a given dimension. And so this becomes a problem. The other issue is, and this is what the voids look like within the material when they form, is that you'll embrittle the material. And so it'll become easily fractured after it's been irradiated. So this is a big problem. So we've got what we call the AAA solution to self-healing materials. So interfaces that are designed to attract, absorb, and annihilate the defects that we put into the material as a function of irradiation. So what makes an interface a good sink? Well, if you have an interface that's got some extra room at it, that helps. If you've got a low formation energy of defects at interfaces, what that means is that energetically, defects want to move to the interface. And once they're there, if their core or their size is delocalized, which means they get a little bit bigger, it's easier to take a bigger defect next to its opposite type of defect and put them together and have them annihilate because they don't have to move quite as far. So these are the types of things that you want. If you can do this, then you can make radiation and shock damage types tolerant materials. So this is what that cascade looks like if we initiate a cascade in a copper layer. So this is copper and niobium. So the top here in this case is niobium, the bottom is copper, and we've removed all the atoms except for the ones here at the interface. This is actually a shot here of what's going to happen in the niobium, and then this here is sort of a bottom view into the copper material. We'll show it again here. So what you see is that we have this cascade form in the copper. Atoms are moving around. They're not in their happy positions at this point. Same thing in the niobium. And after only a couple of picoseconds, all of the atoms have returned to where they were initially. That is, there are no residual defects afterwards. This material just healed itself. And so what we found is that certain interfaces, such as this one that we just looked at, are efficient sinks for radiation-induced defects. Others are not necessarily. And we'll see that here in a minute as well. So let's talk a little bit about grain boundaries. If we're not talking about a composite such as copper and niobium. Again, this process has an energetic particle coming in towards your boundary. It hits your material. There's a whole mess of atoms displacing in the cascade. After it settles, you've got these different kinds of defects, vacancies and interstitials. They move to the boundary. And hopefully, if everything goes well, we end up with a pristine boundary at the end. In reality, this is what we get out of pure copper that's been irradiated at 450 degrees C. This is our grain boundary here. And you'll notice that we get an area next to the boundary that has no little voids. So the voids are all these white dots. You can see white dots here, white dots here. You get this area next to the boundary called the void depleted zone, where all the voids have moved, all of the defects have been sucked into this boundary. What you find is that in pure copper, at the grain boundary, you get voids there. So that's not good for having a reactor kind of structural material either. If we drop the grain size down to nanocrystalline grains, what we can find is that, sure, you don't get as many voids anymore, but you still have these voids at the boundaries. This is some work published by another one of our postdocs, made the cover of Journal of Materials Research. So what happens if you layer the material? Now, if we start with 135 nanometer thick layers, what you find is that right along copper niobium boundaries here, there are no voids. And also, there are no voids at the copper niobium boundary. There are voids within the copper grains that make up the material. So what happens if we just drop the layer thickness? Well, the answer is that you get no voids. You've added enough layers here and enough interfacial content that work as efficient sinks that now all of those defects are sucked into the boundaries and annihilated. You'll find a couple of voids in thick copper layers here, but all you have to do is just reduce that layer thickness a little bit more, and you've made this material radiation damage tolerant. So I'll go ahead and conclude here. So what we found is that the nanolayered composites, they enhance material performance in mechanical, thermal, or radiation extremes. You can make damage-tolerant materials simply by putting them in these nanolayered architectures. We see that we get these remarkable properties that are due not just to having a lot of interfaces, but it matters what kind of interface you put in. What's the local structure of that interface? So today I talked a lot about copper niobium, but we've also looked at materials such as niobium zirconium, silver copper. They're all model systems for these investigations. They're materials that we know a lot about. The eventual goal here is, of course, you're not going to make your car or your airplane out of these types of materials. The next step here is to make multi-layered steels. Take these interfaces that we have discovered here. We know that they're good for radiation damage. We know they're good for high strength. Take those interfaces, put them into a steel product. Put them into an aluminum product or another engineering alloy. Then you can start making these lightweight, high-strength materials where you can use them as an armor or put them into a nuclear reactor. So with that, I'll go ahead and thank you. I'll thank the CMIME team who actually conducted all of this work, and of course then our inspiration, Iron Man himself. So thank you very much.
So Nathan, that was absolutely terrific and fascinating, and I'm sure there's some questions in the audience. Instead of passing the microphone to you, would you kindly just raise your hand, we'll call on you, shout out your question, Nathan will restate it and give you an answer. So, questions?
Yes?
Have you tested the impact of electrical and magnetic fields on the creation of these various nanolayers?
So not at this point, no. But yeah, you're onto an interesting topic.
What was the question again?
Oh, so the question was, have we looked at the impact of electromagnetic fields on the behaviors of these multilayers? So linking the ideas behind it's sort of like I led into at the beginning of the talk, where that's kind of the combination of where you have functional types of behaviors and structural types of behaviors. And certainly the behavior of defects can be affected by magnetic fields or electromagnetic fields. So we haven't looked at that yet, but there is some work going on at the lab to kind of move towards those types of studies. That's a good question. Yes? Yeah, so we have. So I showed just a small snippet of some of the thermal annealing results that we've done. That particular one was 500 degrees C for 1 hour. We've looked at other temperatures, other combinations of temperature and irradiation. And so we have an entire matrix of these different types of studies. An interesting one, a single result that I didn't show today, is actually if you really crank up the temperature to like 950 degrees centigrade, so almost just within a fraction of the melting point of copper. In the end, the layered structure will break down. But these orientation relationships that I spoke of that define the interface planes, those actually strengthen. And so while it doesn't retain a layered structure, the crystals themselves want to move to a certain orientation. Now the implications of something like that are, well, if we now start with a material that has all the same orientation relationship after this thermal anneal and then roll that a whole bunch of times, what happens then? What does that do to our interfaces? And so, yeah, so these knobs are things that we turn in order to be able to try to create a certain type of interface and then test the properties of that interface. Yes? How big is a nano compared to an atom? So it takes about 4 atoms to make a nanometer. So it's small. And if you think about 1 nanometer, it would take 100,000 nanometers to make 1 hair. And so, yeah, it's tiny, but it's but it's actually amazing that all of these things that happen at such a small length scale, just a few atoms. What it dictates is, if you were just to bend a paperclip, what you're doing is moving these atoms through billions and billions of these different defects, moving through the material. So you're actually nanoengineering when you bend a paperclip. So when you do that at your desk at school and your teacher asks you why you're screwing around, you say, I'm doing nanotechnology. But no, that's an excellent question. Yes?
When is this going to be on YouTube?
That's a question for you.
So as soon as I have this wonderful presentation reviewed, I will be able to put it up on YouTube, and I would say look for it in just a couple weeks, okay? Can I ask you a question?
Sure.
So I'm thinking about not extreme environments, but just wear and tear, like bridges that are built and get rolled over by millions of cars in their lifespan. How does the work that you're doing relate to that sort of just aging related thing? And maybe it's directly related.
Yeah, so in metallurgy, what we call that type of aging is fatigue. And what that means is that you just very slightly load a material many, many millions or billions of times. And after you've done that, a lot of times you'll actually start a crack. And this is the way that 90% of engineering materials will fail. And so we have tested fatigue properties, especially of the physical vapor deposited foils. I didn't show a movie of that today. But what you find is that because fatigue still relies on defects, if you make an interface that can soak up those defects and annihilate it, you can make a material that does not undergo fatigue. And so we've seen that for the very smallest layer thicknesses in the vapor deposited question, or vapor deposited materials. So yeah, it's a good question, certainly. Yes?
What about extreme cold? Would that make a difference?
Yeah, that's also a fantastic question. So materials that when they're exposed to extreme cold will go through what's called a brittle or ductile to brittle transition. So materials that are usually deformable, like iron, if you make them cold enough, they become brittle. This happened to the Liberty ships, I believe, in World War II. They would go through these kinds of transitions. So materials do undergo those types of transitions. We actually are working on that problem because it may be that niobium goes through such a transition. And so doing cryogenic types of tensile tests and seeing, is this material still deformable when you put it in liquid nitrogen? That's something else that, yeah, we're looking at. But yeah, it's a fantastic question if these materials can handle cold. Yes?
So sort of before the nano scale, when you're talking about development, so what would in, so you talk about copper niobium, but
Mm-hmm.
talking about like carbon nanostructures. So
Mm-hmm.
at what level do you decide what's a good element? What
Oh.
are the characteristics of the material you want to use before?
So there's a few ways of approaching this. So the question is yeah. So the question is how do we start picking candidate materials to do this kind of processing, synthesis, and measurements? Well, there's one approach is that through vapor deposition, we can vapor deposit just about anything. You can vapor deposit a metal, a semiconductor, a ceramic, glassy materials, no problem. So in that case, our only limitation and what our thinking usually is what do we think that the defect structure at the interface is going to look like? What are the individual arrangements of atoms going to look like? And so we can go in a systematic fashion and say, all right, if we deposit, say, copper and niobium, we'll get this kind of interface. If we do aluminum and titanium nitride, which is work that actually Sid Pathak does, he's also sitting here, can we start doing things where we change the properties of those types of materials? In his case, what he's able to do is make titanium nitride, which is a brittle ceramic. You can start making those materials ductile and deformable. So you can imagine if you could make a ceramic, something that's super hard, also deformable, then you're again making another type of indestructible material. So that's one approach. The other approach is this roll bonding technique. That's a little bit more limited in what types of material systems we can pick. As a kind of a rule of thumb, you have to start with two materials that have a strength that are within about a factor of 5 of each other. If they're off by more than that, one of them will fracture and break up, and then you'll end up with little broken platelets within a matrix. And so we try to find as many different types of systems that we can that will undergo the roll bonding process. Zirconium niobium is one of them, copper niobium is one of them. You can also roll silver copper to large extents. So there are a handful of different ones, but the rules are slightly different. If you want to be able to imagine making any interface you want, you start with the physical vapor deposition and then move on to trying to do something with a severe plastic deformation technique.
Well, let's thank Nathan.
Oh, one more.
Oh, one more, okay.
Yes.
Is there any difference between using organic or inorganic materials?
So yes. So you can also, so the question is there a difference between using organic or inorganic materials? So I assume you're meaning things like polymers, if you wanted to use, if you wanted to compare, say, metals to ceramics to polymers. So yeah, there definitely is a difference. In this case, the slip that occurs in metals is what we're really kind of going for here. So these defects such as dislocations, those occur mainly in metals and ceramics. Polymers are more complicated in terms of the way that they deform in terms of fundamental mechanisms. And so they would deform differently, but yeah, we haven't been doing that specifically with the work that we're doing. Yeah.
Okay, thank you so very much, Nathan.
All right. Thank you very much.